In this session, we're going to talk about an important tool in dynamics called the free body diagram, and learn how to draw them and how to use them effectively to solve dynamics problems. First, let's warm up with this little problem here. An object on a rope is lowered at a steadily decreasing speed. Which is true? Here, if it's a steadily decreasing speed, then the acceleration must be upward, because decreasing speed means acceleration is opposite to velocity. And if it's heading downward but getting slower, it must be accelerating upward, which means the net force by second law, F net, is upward. But there are only two forces acting here, the tension and the rope. And so we see the rope must be the greater one, so that the net force points up. Okay, a useful graphical tool in dynamics is called the free body diagram. It shows all the forces acting on a single object. The object is drawn so-called free, that is, not attached to anything. The effects of ropes, springs, etc., if any, is shown via the forces they exert, not by direct connection. Also, things that are in contact are not shown as being in contact, so as again have only the forces on an object. How to draw free body diagrams the college board way. Draw a dot for the object. This would represent the center of mass of the object, a concept we'll talk about a little bit later, but it's basically the place where forces act, or act as if they're acting. Draw force vectors that each start on the object and point away from the object in the direction that the force acts. Always draw the weight first, and then draw a force or forces for each thing in contact with the object. In mechanics, we're only going to talk about gravity as the only non-contact force, so you should draw it because it's always there and it's embarrassing to leave out. And after you've drawn it, you can just check off all the other objects that are in contact until you run out of them. Very important from college board point of view, do not draw components unless explicitly asked to. In general, they'll be very explicit to not to draw the components. They want the total actual force. Although not part of the free body diagram, you might find it useful to sketch these other things true, such as the velocity and acceleration if you know them, or at least know their direction, and the net force if you know its direction. But, and this is really important, do not attach any of these to the dot, because the things attached to the dot should only be forces acting on that object. As an example, we might take this situation, a relatively standard one, where we have two boxes in contact, A and B. We'll put them on a frictionless surface to make life a little easier for us, and then let's say that we push on A to the right with some force. And let's draw the free body diagrams. In this case, we would have object A and object B separate. And it would say, what acts on A? Well, there's certainly a gravitational force on object A, and there's certainly a gravitational force on object B. Really quick aside, note that we have to give them different names, GA and GB, or whatever you want to call them, but different because symbols that have the same name should have the same value, and we have no particular reason to think that the weight of A equals the weight of B, so we will not give them the equal names. Later on, we'll see this is very important, that only forces that are known to have the same numerical value should be, that are for physical reasons are known to have the same numerical value, should have the same sign. All right, object A also suffers, well, there's the push, whoever's pushing on this thing, person P, and is pushing it to the right, and by college board standards, we should draw the dot at the arrow as pointing away from the dot. I actually find this not the most intuitive way to do it, but they've become very consistent about asking for it this way, so we'll practice it that way. All right, and then what else is in contact with object A? Well, object B is in contact with object A. Object B exerts a force here. I'll call that right now the force of B acting on A. And then we go to object B and we say, well, there's the weight, just like we did. And then, oh, actually, we actually lost one other one for object A. Object A is in contact with the table, and that exerts a normal force, which I'm going to call F and A. Object B feels the weight as drawn, And then also it's in contact with a table, which I'm going to call F and B. Again, no reason to think that that would be the same as for object A, so we'll give it a different name. And then object A is in contact, and it exerts a force on B, pushing it this way, object A on B. And since there's only things in contact with B, that's all we get. Notice very especially here, FP does not act on B because the hand pushing the box is not in contact with box B. So it should not show up on our free body diagram. All right, an elevator lifted by a cable is moving upward and slowing. Which is the correct free body diagram? Well, since it's moving upward but slowing, the actual acceleration is downward. So the net force is downward. So the downward forces have to exceed the upward forces. If we look carefully, in B, the upward force is equal to the downward force. In A, the upward force is more. In C, the upward force is less. Then we have these two other cases where we have the upward force and the force of the elevator. And then finally, F net equals 0 for E. And we can start eliminating some of these. This one is right off. It is slowing. It has an acceleration. The net force can't be 0. Turns out this one's also out because what the heck is this? The force of the elevator. There's got to be a physical object creating a force on the elevator. In this case, the cable, and of course the earth. But the elevator can't create forces on itself, so that one's out. And then we see that the net force has to be C, because the free body diagram would have looked something like this. Well, I guess we're looking at, but we would have F of the cable, because that's in contact, and FG, because it's near the surface of the earth. A ball has been tossed straight up. What is the correct free body diagram just after the ball has left the hand? Ignore air resistance. So to draw a free body diagram, remember we start with a dot, the black dot. We draw in a weight, and then we draw forces for anything else in contact. Oh, wait a minute. There's nothing else in contact. There's nothing touching this ball anymore. It's left the hand. Therefore, this is the free body diagram, and we can see that that's the same as D. A ball hanging from the ceiling by a string is pulled back and released. What is the correct free body diagram just after its release? Well, again, we'll just draw and then compare. Free body diagram, we start always with gravity pointing downward. Then we say what else is in contact with the ball? Well, the string is in contact with the ball and it exerts a tension which is parallel to the string, so it would be something like that. And nothing else is in contact with the ball, so that's the free body diagram, and we can see that that is clearly case B. Fergus is bungee jumping and has stretched the bungee cord as far as it will go. Draw a free body diagram for him. Of course, we know that the next thing that's going to happen is Fergus is going to jump or snap upward again because he stretched as far as possible. So there must be some sort of acceleration on Fergus at that moment pointing up. To draw a free body diagram, we start off with gravity. So there's his weight. And then we'd have the tension in the string, or the cord that's attached to him. Since we know that it accelerates upward, it should be more than gravity. And there's nothing else in contact with Fergus, so that would be it. That would be his complete free body diagram. Someone has given your textbook a shove and is sliding across a level table. Draw a free body diagram for it. Notice the table. Notice the direction of the velocity as drawn. So what's in contact with the textbook? Well, I guess not in contact, but before we do any contact forces, let's start with gravity, pulling it downward. What's in contact with it? Well, there's a normal force from the table, pushing it upward. But there's also a frictional force, and that frictional force, remember, will oppose the relative motion of these surfaces. Since they're moving to the left, the frictional force has to push to the right. So there's some frictional force, and since it's actually sliding, that would be kinetic frictional force. And that would be your free body diagram. This car is parked on a hill. Draw the free body diagram for it. We draw the weight first, and then we say everything in contact. Well, in contact is the street, which exerts a normal force, but also exerts a frictional force, and that frictional force must point up the hill to counteract its tendency to slide down the hill, and that would be a static frictional force. There's actually something kind of neat going on here when we draw these forces. We know that there's a gravitational force, and we know we add the normal force, which let's say goes like this, so we're saying that the incline went something like that. And then we have the frictional force, and we know that they're going to add up like that because the net force is 0. It's parked on the street. It's not going anywhere, so there's no acceleration. So we know that these three forces need to form a right triangle, or form a triangle, and from their construction it's a right triangle. So we know that we have the weight pulling down and the normal force pushing out that way, and the static frictional force pushing up, and they must form a complete right triangle. That will be kind of useful in things we do in the future. It's an additional thing beyond just drawing the diagram, but if we draw it properly scaled, they would form a triangle like this.